So the first question, like I said, is going to be finding the dot product of those two. So the very first thing that we should do is, well, set up those two vectors in our MATLAB, right? So you will do A, or capital A, is equal to 1, 2, 3, 4, right? And then semicolon that one down. And then the other one, which I do not recall the numbers, was B is equal to 12, 20, 15, and then 7, it appears. So now they have been created, which is good. And then it just says use the dot product to find the dot product of the following vectors. So you will just do dot, and then it's A, comma, B, right? Although it's going to ask me to save, so apologies. I have to do that really fast. So let's do Wednesday special, whatever. And the answer is 125. So for the Wednesday special, 125 as our answer. And now we're going to do it the longer way to confirm if our answer is correct. So then it says find the dot product of A and B by summing the array of products of A and B. So the answer is pretty much just the following. You just do, oh, I should go up here. You do sum, and then inside of here you do A dot multiply B. And so this one should also give you, I have to make it a variable. Let's do total is equal to that. And so you get total is 125 as well. So our two answers match, so therefore we've done it right. So this right here, total, the one that I set up as the sum of A times B, is essentially is just the dot product, right? I mean, it's the longer way to do it because it uses the actual definition of it. It just sums them as they go. But this one is the function dot, and it has that inside of it. So there's two ways to do it. Obviously, the dot product way is faster with just dot, but just to confirm our answer, 125 is the answer. So good for us. We've done it, guys. And then the second problem, or third problem, I guess now, since those were really easy, it's very hard to find a question that involves the dot product. That was hard. So, and then the last one, it's a word problem. It says, a group of friends went to a local fast food establishment. Probably not right now, but they did it sometime. It said they ordered 4 hamburgers at 99 cents each, 3 soft drinks at $1.49, 1 milkshake at $2.50, 2 orders of fries at $9.99, and 2 orders of onion rings at $1.29. Use the dot product to determine the bill. So what we have to do is, once again, you just need to make the same thing that you just did before, but only in inside of with those numbers. Sorry. So what you need to do is you need to set this up. So let's do food would be equal to. So there were 4 hamburgers. Sorry, hit a V. There were 3 soft drinks. So 3. 1 milkshake. 2 orders of fries. And 2 orders of onion rings. So 4, 3, 1, 2, 2, right? And then let's do cost. You then set that up as well. And you do 0.99, 149, 250, 0.99. And the last one was 129. So essentially we're setting up the exact same thing as we did before, only using a word problem, which is their food and what they order, or how much it cost, right? But I'm going to semicolon these out so we don't have to see the answer in the command window. And then you do dot food and cost and see what we get here. So it says that the answer we get for total was $15.49. And you can probably do this with a calculator really fast. I don't know if I have one with me. I don't even know if that answer's right. I will look right now, though. Calculator has gone missing. Oh, come on. Nope. Here it is. If somebody beats me to it, you're more than welcome. It was inside of a drawer next to me. So 4 times 0.99 plus. Why did it sound like I was going through the wardrobe and going to Narnia? Yeah. Going through a World War I submarine. Well, yeah, U-boat. Anyway, I was gonna go sink the Lusitania. 1549 is the answer I got on my calculator. So mission accomplished, boys. We can go home. Oh, and lady. Sorry. There's always one. So now we have finished the dot product because, like I said, I don't think that the dot product is hard to find questions that makes this difficult. So I'm sorry to say that these are about the most difficult ones you can find unless they're a word problem, and the word problem ones tend to not be difficult. You just have to know which ones to put inside the vectors. So there's not much more I could do there. But going to move on to the next set of questions. Yes, Blake. Yeah, it's pretty straightforward. There's not much I can get you on that one. Let's go to determinants. So this is our next section right here. So it is practice exercise 10.3. Find the inverse of the following magic matrices, both by using inverse and by raising it to the -1 power to check your answer. So we're going to do magic A, 3, 4, and 5 for the first one. So we should do this. You can do the following. So this is how you would set this up if you were to find the inverse of it. So you would do inverse, and then you'd whatever the name of the matrix is in here. I'm going to put magic 3 because that's the one that we need to do. And then we need to do inverse magic 4, right? And then you do inverse magic 5. And then you need to do the exact same thing, only by raising it to the -1 power. So magic 3 up, -1, magic 4 up, -1, magic 5. And let's see what the answers look like. So I'm going to go ahead and semicolon all these out because I don't want to keep seeing them. Ooh. Close to singular or too badly scaled. So, where is the first magic matrix? So, the inverse... I probably should have done these one at a time to know which one's going to mess up. Let's try that again. So, matrix is close to singular or badly scaled. Probably true. So we have the answer here. So this is the first one. So the inverse of the magic 3 is this right here. And then raising it to the -1 power gets you here. So these are the two answers. And I know these are right. But it is giving you a warning. So, wonder why though. Because I didn't get that warning yesterday. Let me see. This can happen for a number including typographical errors, unmatched parentheses, or editing errors. Huh, okay. Now I'm going to go ahead and mark this one off, and I'll do the middle one so we can see that one. So, as you guys can see, these two add up as well, and they match, so good for us. It has worked, although it is still giving us a little bit of an error here. But it's just a warning. It's not saying that it's wrong. It's just a warning that it's close to singular. And then the last one should be the same as well. 5 by 5. All these numbers should match. So that was basically this question as well. Once again, hard to hard to find something that is that difficult about that. But then we have to do determinants. So we have to find the determinant of each of the matrices in this exercise. So I'm going to go ahead and remove this bottom part. Remove this. I'm getting a phone call. Does anybody else get phone calls from like just random places in the world? I do. And Magic 3. So essentially what Magic 3 means is that it's a magic, you're creating a magic matrix. A magic matrix is that in all directions they add up to the same number. So here, for example, if you see magic matrix here, you'll see 8, 1, and 6, which adds up to 15, right? 8, 3, and 4 adds up to 15. So in all directions it adds up to 15. So it's a special matrix. Even diagonally, it adds up. So Magic 3 was that. So I'm going to go ahead and shut that one off. I don't know why 15. I think maybe that's just the number that it can actually be done. Well, I mean, I feel like it could be done with all of them. So I don't know why it does 15. It's a good question. Maybe I'd have to go back and look in the magic matrix chapter, because we did talk about it very briefly though. So that says determinant of each of the matrices. Gotcha. So it is determinant. So you do determinant magic 3, and let's see if that comes up. So you get the answer for the determinant of magic. Magic 3 is negative 360, and then you do determinant magic 4, and then determinant magic 5. I'll take this one off again. Yeah, something about that doesn't seem right. Although, maybe they are right. I mean, the thing is that it has to. I mean, if it's the magic matrix and you did determinant of it, I mean, those numbers seem really weird, but maybe. I mean, it seems like it might be the answer. But essentially, this right here is the path, right? Is determinant is the DET function, and you just put whatever your matrix is inside of it. I don't have, like I said, so the practice problems that we're doing right now, the answers don't come in like an actual copy of it. You have to put in their code in MATLAB. But their code, I did it last night, looks exactly like this. I just can't remember what the answer was. So, but I know the first one's right, because negative 360 is what I got last night too. So once again, now we have to move on to the last part of it, which is consider the following matrix. So I want you guys to answer this one. Would you expect this matrix to be singular or not? And if you recall, what singular means was, does it have a determinant? Yeah, I thought so too. But Lonnie probably knows better than me, because, he took that very, very annoying class. But I'm gonna go ahead and just call this one C, and we're gonna find out, because I actually didn't do this one last night because I was like, it's kind of, and then we have 2, 5, 6, and then we have 3, 6, and then 9. So there is our matrix, and then I want to do the determinant of C. So it says C is 1, 4, 3, 2, 5, 6, 3, 6, 9, and you get 1 put. Dude, that's something about that seems so weird. So it looks like it is. I'm actually going to do the inverse. So inverse, oh. So I think I know what the question is, more or less, like what it's asking. Yeah, okay. So when we were getting this number right here, or this thing, is that essentially it's close to singular, because if you look at our determinant answer here, it's 1.5 to the negative 15, which is what? How close is 1.5 times 10 to the negative 18 to 0? It's pretty close, right? I mean, we're talking, what is it, 14 zeros in there. So essentially, yeah, it's really close to 0. And so MATLAB is telling you that it's really close to 0, or it's badly scaled. But it looks like it does have a determinant, and it does have an inverse, so it does work. But it's really close, apparently. Yeah, it's really, really close. But yeah, once again, there's not many more difficult questions I can find for this. Your homework, if you haven't looked at it yet, is a lot of very. You guys will probably feel like it's just really dumb. So I hope not, though. But I tried to find the engineering questions in there, and we're gonna get to one in just a second. I did bring an engineering question into this as well. Where is it? So, and you guys should pay special attention for this one, because if anyone's actually looked at the homework yet, this question will look very familiar. So this question right here is something that you actually do have on your homework, except it's just a little different. But this is the exact same question, more or less. So it says, example 10.4, moment of force about a point. So this is your statics days coming back, although you might be in statics. I don't know what the 4-year plan looks like anymore. But it says, the moment of, and I was never on it to begin with, so the moment of a force about a point is found by computing the cross product of a vector that defines the position of the force with respect to a point with the vector force vector. Consider the force applied at the end of a lever as shown on figure 10.4. So we have applied force. Here's the lever. If you apply a force to the lever close to the pivot point, the effect is different than when you apply it further out on the lever. Yes, I think we can all agree on that. That moment, or that effect, is called the moment, right? And then it says, the force applied to the lever creates a moment about the pivot point. Calculate the moment about the pivot point on a lever for a force described as a vector. So we've got this right here, right? So this is our force vector. So we can put that in as well. And it says that assume that the lever is 12 inches long at an angle of 45 degrees from the horizontal. All right. So we have to do so we now, what, you talk about the moment equation? You wouldn't remember that one? So I'm going to do F. So the F for this is, it was negative 100, 20, and then 0, because we had nothing going in the z direction. So we have negative 100, 20, 0 is our force vector, right? So now we need to find our r. So remember, because we're trying to do r cross f, which is the moment, right? So we now have to find the r. Now that we have the f, we need the r. So to do this one, we need to do some trigonometry here. Now, the answer is right below us anyway, but I was just going to show you how you do it regardless. Let me pull up Epic Pen. It's going to be easier to do it on here. So I think for your homework, you're going to have to do a little bit as well. But let me go ahead and just draw this out. So this is theta. We're back in trig, guys. So this right here is where the force is being applied. I'm just going to write that as a little dot. So essentially what you need to do is, because this is a 45 degree angle, the x and the y are in the exact, they're the exact same. It is the displacement. from that center, from this middle point, is the same because we're in the middle, 45 degrees. So we just need to find x or y, either one. So if you write this out, I'll just do the x. So we're going to call this x. It does. It said in the question is a 45 degree angle. So you would do cosine of 45 is equal to adjacent over hypotenuse, right? Which adjacent to this angle would be x. So you're going to call this one, I'm just going to call it x, over hypotenuse, which they said was 12 inches, right? So cosine of 45 is root 2 over 2, if I recall. I think that's correct, root 2 over 2. I'll break the calculator out in front of me. Pretty sure it's root 2 over 2 though. So it should be 12 times 0.7071, I think is what root 2 over 2 actually equals. But you never truly know. Problem is that this calculator, I absolutely despise how difficult it is. See, it's in radians. Oh my god. Okay, we'll trust you then. We will trust you. So we have cosine of 45 gets you 0.7071, right? And then you multiply it by 12, and that gets you x, the x direction, right? So this one is 12 times 0.7071. So it's I got 8.48. So here in a second we'll take a look. So if we go back to here, I'll get rid of this off the screen though, because so what they got was they did 12 divided by root 2 how they did it. But if you do 12 divided by root 2, you get 8.48. So it's the exact same number. They just left theirs in this long form right here. So they have 12 over, or so they have 8.48, which is what we got. But once again, just plug that in here. So our x direction to this applied force is 8.48. And our y direction is 8.48 as well, because we're at 45 degrees. So these two are the exact same length, right? And then the last one is k. There is nothing in the k direction because we are not taking anything in the z, right, going into the page. We're not taking that into account. So this is our r vector, which is this. So I will go ahead and put this into the MATLAB. So r is equal to 8.48. And then we have 8.48 and then 0, right? You could leave it. You could do the same thing. You could do 12 over root 2 if you wanted to, but I'm going to reduce it. And then you'd have the last one. The last part of this was that we just need to do r cross f. Let me get rid of the black spot off the middle of the screen. So then we have to do r cross f. So you do cross is the name of the function, and you do r and f, and see what that gets us. I don't think. One sec. I need to get rid of all these other things behind me. It's starting to clog up the screen. So r is this. Yep. So it says that this should be 1,000. So it's 1,000 and one. Yeah. So it's 1.0 times. So it's times 1,000. So 1.0176 times 1,000, and you get 1,017. So our moment our moment is 1,017, and this should be in what, like what is it, like something inches? I don't even remember what moments go in. We actually don't even know, do we? Because they didn't give us what the force was in, but I assume it was in what, foot-pounds or something, or yeah, whatever it would be. I don't remember much about stack. Well, no, it wouldn't be in newtons because we're using inches and everything. It could be in newtons. You just have to convert it. But it doesn't really matter at this point. But our answer is 1,017. So this question is you're going to have to do this exact same thing on the homework. So, yeah. Hopefully this was helpful and you paid attention. So, yeah, the question didn't tell us that information, but if it's in English, you can assume. I think it's in pound force, right? All right, so then we move on to another question, which I think I have is the last one. So the last one we're going to do is, it's actually in the problem section. So solving systems of linear equations. So this is the last one that I thought would be like super relevant to you guys. So right here actually is another engineering sort of related question, but this isn't the one that we did. The one that this looks, this is just like a truss. So that'd be cool. So it's solving forces in a truss. Could be useful. But this is the one that we're doing just to show the basics of how you do it. So solving systems of linear equations, right? So how we do this one is we have to first set up these in our matrix. So this is for part A. So part A is these two. So it's only a system of two equations. So if we go back, I'm going to move this over though so I can read it while I do it. Let me go ahead and get this. So the first one is negative 2x plus y is equal to 3x, right? Or 3, sorry. They're close together. So we're going to call this one, I don't know. What do we call this one? D. I don't know what to call this one. We'll just call it, I just don't want to reuse things just to make it less confusing. So we'll call it D is equal to, we have negative 2, 1. Yeah, negative 2 and 1. And then we do semicolon, and we do 1 and 1, or 1 comma 1, sorry. And then E is equal to another one, which is 3. But remember, this one has to go down immediately. It's a column matrix. So 3 and 10, right? So let me actually go ahead and just see what these look like. So this is what they should look like. So for our two equation matrix, you have 2 by 2 and a 1 by 2. So now we just have to solve the problem, right? So how do you solve the question? Anybody know? Anybody know what you have to do here? Wait, what was this, Blake? What did it say? You're saying, so each of the equations were equal to what? And A are equal to each other. No, they're not equal to each other. They just, so for some reason, they drew this one. Here, I'll put it on the page. They drew this one on the same line. So these are two separate equations. It's just they drew them on the same line. These were all drawn down. Yeah, it's once again, not a great way to do that question. So, does anybody know what we have to do now? Taking a guess here, anybody? Yes. So essentially, what we have to do is that we have to find, we have to use an inverse command, right? So, and there's two ways to do this. If you recall from the textbook, there were two ways to do it. There was the dividing way, which I think, Lonnie, you said was which type of... So there was one where you divide them out, and then there was one where you do an inverse. I don't remember what the name of that other one was. He's the master of this. So... But essentially, we have to do set up a variable, and you set it equal to inverse of your main matrix D, which is D in our case, times B. Hey, we all need to be flattered sometimes. Oh, not down here. What am I doing? Type it in the command window. So I'm gonna say you can call it x, whatever it is. The final, you can just call it result, is equal to, and you want to do inverse of a, or not a, for our case it's d, times f, or e, sorry. Thought it was f. So inverse d times e. And what this will get you is, hopefully, it gets you our answers for where x is equal to one of these. So x will be equal to 2.33 and y is equal to 7.667. So that is the solution for the system of equations. So right, you create your matrices like this, and then you do an inverse to solve it. Or there's another way to do it. You can do this one. You can do I'm gonna call this one y. Actually, G. You could do it like this as well, which is I can't remember which one in the book did this one, but it was D over E. Oh, that wasn't it. Is it D over E? Yeah, it was. So why didn't this one work? D. Oh, it was the wrong backslash. Ugh, that's why. There it is. So you get G is equal to the same thing. So this was also in the text as well, that you have to use the wrong other backslash. We did do this one, I promise. There was a bunch of different types of them. And after I do this next one, I'll go back and show. Yeah, I overlook it immediately, like all the time. And now I have to do the next one. So the next one is, let me pull that up. The next one is this one. So it's 5x plus 3y minus 3z. So this one is going to have 3 variables in it. So I will move this over here so I can type it easier. So for the first one, we're going to call it f is equal to 5, 3, negative 1. And then it's going to be 3, 2, I don't like them, not space, 2, 1, and it's going to be 4, negative 1, 3, and that ends it. So that is our first matrix, and that is the coefficient matrix. So if anybody knows, like doing your matrices, this is the coefficients of the actual equations. So 5, 3, negative 1, 3, 2, and 1, and 4, negative 1, 3. Now, last one, or next part, is we have to do the exact same thing. We have to set up a column matrix with your what it's equal to. So we're going to call this one H is equal to, this should be 10, didn't put it in there, 10, 4, and 12. So you have H is equal to 10, 4, and 12 because that is what our equations are equal to, right? So 10, 4, and 12. And then, pretty similar as the last one, you just say that answer is equal to F. You would say inverse F, so inverse of F times H. And you should get something, although I'm going to get rid of all these again. Give me a second. And it says F was equal to this, H is equal to that, and our answers are for the what each value is equal to, they're equal to this. So no more doing long matrices, and I know your calculator is capable of this as well, so I am aware. But it's easier to type them in on here. And then we don't really have to do the last one. What time is it? It's 41. We won't do the last one. The last one is the exact same thing, except there's one more. It's 4 now instead of 3. So not really much to talk about there. But there's one thing I did want to show you because, where was it at? No, it wasn't in here. It was in solving systems. Yeah. What each value in F I am recording the example classes. So, we are currently recorded. Sorry, all of you. I didn't ask. But, yes. So, this one right here was, so these were the different types. These were solving systems. So the first one was inverse matrix. And then the second one was left division. And then the last one was that row echelon. So these were the three methods by which we did them in the class, but I mean, honestly, you can, and I know, so in the homework, you will have to do, I think you have to do them different, in a different method. If anyone's looked at the homework, I mean, if you have or if you haven't. The last question, it says, in general, matrix left division is faster and more accurate than matrix inverse method. Using both techniques, solve the following system of equations and time the execution of the script with the tick and tock functions. If there's no difference, that means your computer is fast enough to not make it matter. So what you're going to have to do is you're going to have to do this system of equations, type this in, and then you're going to have to time your solution. So you'll put tick and tock right before and after where this is going to execute, and then you'll do it for the other one as well. And you should get two different time numbers, and those two time numbers will be the comparison of why matrix left division is faster than the other one. But this is matrix left division, just so we go back to that really fast. I think that's the one where you divide it out. Let me see. Yeah, it was this. It's the one where you divide it out. So I've showed you how to do both of those. So hopefully that will be a pretty easy question. And you said, what did each value in f correspond to? Was the first row of values from the first equation, or was it all the rows? So if you go back up here, f is the coefficient of each one of these. So I'll pull it up here. Let's go to the problems. Systems linear equations, got it. So, right here. So f, I'm going to move this over here. So f corresponds to the coefficients of each one of these in this. So think about if you were making an actual matrix solving equations, you would do this, right? And you would go down the line and you would go, okay, you have 5, 3, -1. And then you'd go down for your next equation, which would be 3, 2, 1. And then it would be 4, -1, 3, right? These are the coefficients of this right here. And you take a step down for each equation you finish. And then in here, right, is your variable matrix, so it's x, y, and z. And then over here is supposed to equal to whatever the equations were equal to, which was 10 for your first equation. So 5, 3, -1, x, and then 10. 10 was the first equation. This one, the next one, was 4, and the last one was 12. So this is how you would set this up in actuality, like by hand. This is what it would look like. But for you inside of here, it looks weird because of how it, so what I could have done here is I could have done this. And that would be how the matrix looks. It doesn't change anything, me doing that. It's the exact same matrix as before, as long as you use the semicolons to space them down. It means the semicolon means it's a new row. Yeah. So you could have written it like this as well. The reason why was because, yeah, it's part of the technique. So if you go back up here, I'll pull this back up as well. So it's solution using the matrix inverse. So if you remember, we talked about this one, is that essentially it's sort of by using the matrix inverse, if anyone, so I know we have a couple people that were doing numerical methods or something. Essentially what it's doing is that by multiplying by the inverse of the matrix, I I had to do these by hand, and it really sucked. You do get the solution because what it leaves is it leaves just the solution at the end of it by multiplication. So I'm gonna see if there's like a better way to show this in here. Although they don't really go into depth of how it works specifically because it's a computer class. But let me see if it actually like says. So it says the most straightforward way of solving the systems is matrix inverse. It says since we know that A inverse times A is equal to 1, right? Because they undo each other. You remember we made this thing with like it was the natural log and times E gets you this number at the top, whatever it was raised to. So it says if we multiply both sides of the matrix equation, AX is equal to B by -1, right? So you have A inverse times A of X is equal to A inverse of B. And so, by doing that, you end up getting rid of both of the A's and you leave 1 here. X is equal to A inverse times B. And then it says, since A is a 3 by 3 matrix, its inverse is also a 3 by 3 matrix. And it says the multiplication of A inverse times B, which is the reason why it has to be a column matrix, is because remember, these have to line up. The multiplication, if you remember in our very first section, it was the multiplication chapter. They have to be, essentially, these two middle ones have to equal up. They have to be the same. And it says it works up. So it says if you change the order, it will no longer match. So you have to do it in this way. So yeah, that's basically it. That was more or less all they talked about in this chapter. But if you want like a more in-depth method of how they do it, they would teach that in numerical methods. And to be honest with you, I'm so far removed from numerical methods, I wouldn't feel comfortable even trying right now. So it's been a long time, guys. Probably 2015. So. But if there are no more questions, I will end the video. I'll take attendance and then we can go.